Let's have a look at some more examples of finding stationary points given some more complicated functions, I guess. In example 4, we have a function defined by the rule x ln x plus a plus 1. So it looks like we have a couple of translations going on there for the ln bit, but we've also got x multiplied by as well. So it's not a function that we can probably intuitively just know what the graph looks like. Of course, we could graph it if we had technology, but without it, let's see if we can find the stationary points if they exist. Well, it must do, because it says it has a stationary point at x equals 0. So that's a bonus. Find the value of a. Now, clearly, I can't just put in the value of x equals 0 here and here, because that doesn't really tell me much at all, really. So I need to use the differentiation rules in order to move forward with this. So let's have a go at this problem. We're going to go dy by dx, and as we do that, we will see that this will have to be differentiated, and then the 1 will disappear because it's a constant number, so the derivative of 1 is 0. So let's just focus on this bit here. It's x times ln x plus a. There's really not much else we can do other than use the product rule in order to work that out. So let's do that. It doesn't look too hard. U is equal to x, so u dash is equal to 1. Easy. V equals the ln of x plus a, and v dash is equal to 1 on x plus a. And using the chain rule, the derivative of x plus a is just 1, so there's no need to go any further than that. So inside out, we've got dy by dx equaling 1 multiplied by ln of x plus a, like so. And then the outside would be x multiplied by 1 on x plus a, so that would be x over x plus a, like so. And it's a stationary point, so that's going to equal 0. Okay, that looks complicated, but it's not too bad because we just need to use that extra bit of information to simplify what we're seeing, and that is x is equal to 0. Okay, so if we go 0, we've got here a 0 here for x, and that would make that ln of a. So I'll have ln of a. And then this whole big, messy, complicated thing here is going to be 0 on the top here, divided by a. And anything, if we divide 0 by anything, we just get 0, and we're assuming a is not 0. So that just disappears. So we end up with actually ln a is equal to 0. What does that mean? Well, just a reminder, that means log base e of a is equal to 0, which means that a is equal to the e to the power of 0, using our basic definition of a log, i.e. a is equal to 1. So it looked complicated, but actually it's not. So the function is actually y equals x ln x plus 1 plus 1. Alrighty, let's have a look at a couple more. Find the values of a, b, and c of that quadratic function there, given a turning point. We can say turning point because it's a quadratic, so we know the kind of stationary point it is, at 1, 2, and that the curve passes through the origin. So we've got 3 unknowns there, we've got 2 facts, we can sort it out from there. It's actually 3 facts if you think about it. It's a coordinate, 1, 2, plus it's also a turning point, so we can put all that together. So let's have a look at point number 1, I suppose. Point number 1 is that the curve passes through the origin. Now, that means, visually, I don't know whether it goes up or down. It could be concave up, concave down, but I know that the curve is going to pass through here, which means that it must have an x and a y intercept of 0, 0, right? So we can say that y-intercept is equal to 0, 0, therefore c must be equal to 0. Nice, done. Okay, number 2. What else we got? A turning point of 1, 2. So we know that y passes through, the function, the curve passes through 1, 2, because it's a turning point, so that's part of the curve. But let's go for the derivative first, dy by dx, and that gives us 2ax plus b, and the c, being a constant value, disappears. P.S. we know that c is 0 now, so it's disappeared one way or the other. And because it's a turning point, that is equal to 0. Okay. When x equals 1. So we have 2a plus b is equal to 0. Okay, using that fact that the turning point is at 1, 2. So there is a an equation. We also know that y is equal to, I'll go even further than that. We also know that 2, the y coordinate of the turning point, must be equal to ax squared plus bx plus c, where x equals 1. So we're going to have a times 1 squared plus b times 1 plus c, which we know is 0. So we've got 2 is equal to a plus b, and that is a second equation. 2 equations, 2 unknowns, we can solve that. So I am going to go, let me see now, 1 minus 2, like so. So let me line them up. I think it's important to not do this in your head if you can handle it, because it's easy to make silly little mistakes. I've got 2a plus b is equal to 0, and then I'm just going to reorder this so they're in order of same term. So a plus b is equal to 2. And I am subtracting those, and that gives me 2a minus a is a, b minus b is 0, and 0 minus 2 is negative 2. So we've got a is equal to negative 2. Hooray! Now I'm going to substitute a equals negative 2 into one of the equations. Doesn't matter which one, I'll do it into equation 1. So we've got 2 multiplied by negative 2 plus b is equal to 0. So 2 times negative 2 is negative 4. Add negative 4 to both sides to get b is equal to 4. So it says find the values of a, b, and c. So we can summarize by saying, therefore, a is equal to negative 2, b is equal to 4, c is equal to 0. It's really important to summarize at the end, even in an exam, because the more you can highlight where your answer lies, the easier you're making it for the examiner to find marks for you. They have to hunt for them and they miss them, then, things can happen. So as much as you can, try and make it nice and clear for the marker. Note that I'm not writing what the equation is. I could do quite easily y equals negative 2x squared plus 4x. I could do that, but it didn't ask for that, so I'm not going to write that down. I'm not going to waste time doing that. If I had time, I could put it into my equation here. What have I got? Minus 2 and 4. Minus 2 plus 4 does equal 2, so the check is done there. So that's cool.